now we've got a bunch of us. We've got like 27 folks in here. That's doing pretty good. Well, let's pull up our algebra and see what it looks like. Oh, let's just talk about our schedule here. We got this week, we've got next week, and then we got finals week. That's it. So if you're missing a bunch of assignments, now is past time to get those turned in because you just had a week off with no new assignments. So hopefully, those of you that were missing stuff, hopefully you got a lot done in the last 10 days. While we didn't have any new assignments, but yeah, we've only got 2 weeks plus finals week. And our final in here, I've got the finals. I got this posted on Google Classroom. Our final will be at noon on Wednesday, December 18th. Noon to 1:55. Yes, Mary.
So will we still meet on the Monday and Tuesday before finals?
That hadn't really been determined yet. I'm sure I'll talk about that in my Thursday meeting this week. All of us virtual teachers have a Thursday meeting, so we'll discuss that. But I don't know. I'm betting that we will, just to see. But we won't have a new lesson or anything. It's finals week, so we'll get that figured out because I was wondering that myself. But our principal hadn't talked about that, and we haven't discussed that. So we got to figure that out soon because we need a plan for that week if we're going to do that Monday and Tuesday. It may be meet Monday and Tuesday for just people that need help getting their grade up before finals or something. We'll see. All right, let me pull this up here. Algebra 2. Let's go to our grade screen, see what's left. Ooh, look at there. We've got polynomial transformations and solving and graphing polynomials. That's what we have this week. Next week, we've got polynomial identities and proofs. And then we have a discussion-based assessment. We haven't done with those since the first unit. So next week, we'll have a discussion-based assessment and one lesson. So we got to get through 403 and 404 today. So let's jump into it. Polynomials, that means something bigger than an x plus 4. It'd be like x squared, x to the third, x to the fourth, anything like that, Polynomial, something with multiple terms. X to a big term. So we're going to describe what characteristics describe even and odd functions. So we're going to just be able to describe those. And how does a constant or a coefficient affect the graph of a polynomial function? So graphing polynomial functions without technology. Like, why would we do that? Well, it's good to know. Graphing on a coordinate plane is adapted along with your skill in math. I mean, we start out, when you first start graphing stuff, you just graph points. Graph the point 4, 1 on this XY table, right? And you would go find where x equaled 4 and where y equaled 1. And you'd put a little dot there. And so that evolved into eventually graphing lines, connecting points. Then we graphed quadratics, making parabolas. And even now we do some kind of weird W-shaped things and other weird things. So let's review on how to graph different functions, like graphing a line. We had an equation like 1/2 x plus 5. We had something like that. We would make a table with our x's. Might choose -6, -4, 2, 0, 2. Or you might do -1, -2, 0, 1, 2. Something like that. And we would substitute each of those x values into the equation, like -6 multiplied by 1/2 plus 5, -3 plus 5, so y equals 2. So we get the point -6, 2, -4, 3, -2, 4, 0, 5, 2, 6. And then we would plot those points and connect them with a line. So we'd find those 5 points with our table and make a line. And so we got pretty good at that. You've done that in many classes in the past. And from that, we would learn later that y equals 1/2 x plus 5. That's slope-intercept form. So that means we could have just gone to the y-intercept of 5 and then used the rise over run instead of having to substitute the x in. The slope is 1/2, so that means go up 1 and go right 2, 1 over 2, and we get the second point at 2, 6, and then we could just draw a line connecting those points. So there was multiple ways to graph a line, especially if it's in slope-intercept form. So that wasn't too bad. Graphing a quadratic equation. So if we were graphing 2x squared minus 8x plus 7, we would find the vertex, right? So we could do that in the standard form, ax squared plus bx plus c. We know what a, b, and c is, and the axis of symmetry, or the x value of the vertex, we can find by negative b over 2a, which in this case, negative b would be a positive 8 over 2 times 2, so 8 over 4, and we know 2 is the x coordinate of the vertex. We can substitute that 2 back into the equation to figure out what the y is. Find the y is negative 1. So now we know the vertex is at 2, negative 1. So that knows where the center of our parabola is. So then to make a table of values, we want 2 to be in the middle, because we know that that is where the vertex of our parabola is. So we would go 0, 1, 2, 3, 4. Substitute the x's in. We already knew what 2 was because we already figured out the negative 1 for the vertex. But when we substitute these other numbers, we get 7, 1, negative 1, 1, and 7. We're not surprised that matches because the parabola looks the same both sides, right? Then we can do those pairs. And once we put those 5 points, we can kind of connect it with the parabola looking shape. We know it's kind of a curved vertex down there. And this one's kind of steep. It's kind of a steep. So we know how to do that. We can graph lines. We can graph parabolas. But let's talk about higher degree. So a third degree polynomial is called a cubic function. So the simplest cubic function is just f of x equals x to the third. So the graph of this is found by choosing some x coordinates and just substituting the equation to get the y values. So like negative 2, negative 1, 0, 1, 2. Substitute those in. So you're basically taking them to the third power. So negative 2 to the third power is negative 8. Negative 1 to the third power is negative 1. 0 is 0. 1 is 1 and 2 is 8. So that gives us these points. We can plot those and then graph it. Once you plot the 5 points, we know that a third degree is going to be curved but going upwards. So that would be the graph of x to the third. So now let's talk about how functions can be translated. This is nothing new. We've done this with quadratics. We've done it with other equations. But if we add a number onto the end, right, whatever the function is, oh, wait, no, this is not onto the end. This one's onto the end. See, the plus c is outside the x. That shifts up and down, right? Shifts up if c is positive, down if c is negative. But when we put it inside with the x, because we did like x squared, and then we made it where the x had a parentheses, x minus 2 in parentheses, squared, and that shifted it to the right 2. Same thing with these other functions. If you put a plus c, it goes left. If you put a minus number like x minus 2, it would go right 2. That's going to work for these x to the third, x to the fourth equations as well. Putting a c in front of it, multiplying the x times a number. That makes it go wider or narrower. It makes it more steep or less steep, right? So if the value of c is a large number, it's going to get really, really steep and really skinny. If it's less than 1, then it's going to spread it out and make it wider. And if it's negative, it's going to reflect it. And then if you put a number out in front of the entire thing, causes the shape to open wider or more narrow. And also, if it's negative, it can reflect downward over the x-axis. So it says, okay, an example. Let's say we want to graph f of x equals x plus 2 to the third power. So it says we need to find the turning point. So the time finding the vertex of a quadratic equation, when finding the vertex of a quadratic equation in general form, the expression inside the parentheses will set equal to 0 to find the x coordinate of the vertex. Well, we can do the same thing here. We can take that x plus 2 and set it equal to 0 and find out that the turning point is going to be at negative 2. So then we can choose points around negative 2, 0, negative 1. There's the negative 2 we wanted, negative 3, negative 4. Substitute that into the equation to get the y values of 8, 1, 0, negative 1, 8. Plot them and connect them in a graph. So there's the negative 8, negative 1, 0, 1, and 8 for the y values. And so basically it's just the regular x to the third, but it's shifted left 2 spots because it was x plus 2. We see it's just shifted left. So translations work exactly the same, even if it's a cubic function or a quartic function. Quartic means to the 4th degree. X to the 4th. Again, make us a table, negative 2, negative 1, 0, 1, 2. Substitute the x values into the equation. Take them to the 4th power to get 16, 1, 0, 1, and 16. Plot those and connect them with a little bit flatter at the end. It's not quite as, it's not quite as curved as the x squared. It gets flatter and flatter the bigger the exponent gets. So you maybe think it looks like a parabola. Well, it kind of does look like a parabola. But here, let's compare them right here. Y equals x squared is a parabola. All right, we'll move that right over there. Now let's look at that compared to an x to the 4th. See, the x to the 4th gets flatter down here at the bottom. It doesn't quite have the same curve as a parabola. So an x to the 4th is not a parabola. A parabola is a very specific shape that's tied to a quadratic equation. So it's flatter at the bottom and it gets steeper than a quadratic equation. So that's a quartic. Example 2. This says, what if we had x to the 4th plus 3 by hand? Well, it should be the exact same thing we just did, except for everything's going to be 3 higher. We'll go ahead and look at it on the graph here. If we did it plus 3, it just raises us up 3. Nothing's different. It's just all the y values are 3 more than they were. Here, I'll compare it to here. Oh, what's it doing now? There you go. There's the x to the 4th. Here's the x to the 4th plus 3. Just shifts it up. If it's a minus 3, it goes down, right? We know that plus and minus just takes it up and down. All right. Will most cubic and quartic functions be this simple? Sure. Let's look at some more polynomial functions. So there's linear. It was just a straight line. Quartic, that was a parabola. Cubic makes that little straightened out S curve, and then the quartic is a little bit flatter than the 4th degree. And look, here's a negative quartic equation. Got a little bit extra stuff going on there, but it still is a 4th degree equation. Both ends point the same way. So here are the things. We're going to write this in our notes again. I think we've had it in our notes before, but we can never have too much of this in our notes because it is very key to understanding what the graph's going to look like. That'll help us know if we type something in wrong or if we just have a question about which end it points. So let's put this in our notes once again. Like I say, you may already have this in your notes, and if you do have them handy, that's great. All right. So we're going to put this back in our notes to figure out the graph of polynomial equations. All right, let's see. Graph of polynomials. All right, let's see. Do they have anything at the top on there? No, it's just the end behaviors, right? And behaviors. All right, that light's too bright right there. Okay, if it is an even function or an odd function, even or odd, that's really our two choices. And what do I mean by even or odd? I mean the highest exponent. Like this would be x squared or x to the 4th or x to the 6th or x to the 8th, et cetera, et cetera, et cetera, right? That it's an even number, largest exponent. that in our notes just to make sure we're all clear. Largest exponent is even. Or if it's odd, it's x. It's x to the third. It's x to the fifth. It's x to the seventh, etc., etc., etc. All right. Need that for third, etc. So if it's even and coefficient, and we're talking about the coefficient for that largest exponent, the coefficient in front of here, positive or negative. That's really our two choices. So if we have an even, like x squared, x to the fourth, x to the eighth, and it has a positive coefficient in the front, left side goes up, right side goes up, like a parabola. If we just have x squared, it's a parabola and both ends are pointing up. If it's got a negative, it's negative 2x squared, both ends are pointing down. Okay. Over here, if it's odd, x to the third, x to the fifth, and we have a positive coefficient. So we got 3x to the third, it's positive 3. The right end will go up, the left end will go down. If it's negative coefficient, just the opposite, left side up, right side down. So let's look at that on Desmos real quick. So this is an x to the fourth, right? If it has a positive coefficient, which it does right now, it's 1. But if we put negative 5, it's a fourth degree, so it's even. It has a negative 5 as a coefficient, so both ends are pointing down. And we see that, both ends pointing down. Let's change this to an odd number. Let's do like x to the 9th, something weird like that. And we could put plus 4x to the 6th plus 2x minus 1. Say we can do that. That just changes what happens in the middle. But nothing changed about the ends. This is a negative coefficient out front. Negative 5. It's a negative coefficient. I guess I'll highlight these over so we don't forget about them. It's a negative coefficient with an odd function. This was an x to the 9th as a negative 5. The left side's going to go up. The right side's going to go down. See, the left side's going up. The right side's going down. What happens in the middle is all by the rest of the equation tells us what happens in the middle. All we're caring about is the end behavior. And we know the y-intercept is going to be the constant, negative 1. If we change this to fifth, I need to change it to a 4 then. 4, 4, and I change this to be a 5th degree. So now it's a 5th degree. Still, it goes up on the left. And change this to a positive coefficient. Instead of negative 5, let's make it positive 2. 2x to the 5th. Now it's an odd, but as a positive. Odd with a positive coefficient goes up on the right side, down on the left, up on the right side, down the left. So we can quickly identify what a graph should look like, at least what the end of the graph should look like, just by knowing, is it odd, is it even, does it have a positive coefficient or a negative coefficient on that largest exponent. So it says, what is the end behavior of 16x to the 4th plus 8x to the 3rd minus 12x squared minus 15x plus 9? It's even. That means both ends point the same way. 16 is a positive, so both ends are pointing up then. Look at the graph. The degree is 4. It's an even number. The ends of the graph will be in the same direction. It's positive. Both ends will continue up. So we knew that. All right, solutions of polynomial equations. The x-intercept of any linear and quadratic equations found by substituting 0 for y and solving for x, right? When we solve quadratics, we set them equal to 0. And then we solved them and found out what the zeros were, and those were the solutions, or at least the real solutions. If we had imaginary solutions, that didn't work. But look here, consider the parent function for the cubic f of x equals x to the third. And observe the graph below. So this is just x to the third, just normally by itself. We can change this to just be what they're showing us there, x to the third. Okay, that's just the standard x to the third equation. What happens to the graph of the parent function when now it's going to x minus 3 in parentheses to the third minus 1? Well, without graphing that, we know the x minus 3 is going to move it to the right 3 spaces. That's going to move it. Well, this is just 1 because they got it blown up. It's going to move it 3 to the right, and that's going to move it down 1. Let's see that over here. Let's see. Oh, that's 2x to the third, just x to the third. Let me change this to go by ones. All right. So now this is just by ones. So if we change this to x minus 3, minus 3. And see, it moved over to the right 3 spaces, and then minus 1. Now our turning point is down here at 3, negative 1. It was at the origin, but it went right 3 and down 1 because we translated it by adding numbers to the equation. So use technology to check that, it says. So, yeah, we know it. And here's what they showed it. It went over to 3 and down to negative 1. Just check your answer. Well, that was, oh, then they substitute that back in there to see it does equal 0. All right, so similar works for 4th degree. Let's look at this graph below. So if we have x to the 4th, what happens when we go negative 5, x plus 1 plus 5? Y equals x to the 4th. There's the regular one. Negative 5, that's going to make it turn upside down because that's a negative coefficient. We want to change it to x plus 1. So that moved it left 1 because that's a plus with that. And then plus 5 is just to move it up. So we moved the vertex from 0, 0 to negative 1, 5 because we added the 1 inside the parentheses, added the 5 at the end. So we knew it was going to point downward because it was a negative coefficient with an even exponent. So, and it looks as we expect it to, and the zeros of the function can be observed from the graph. Look, the graph crosses right here, negative 2 and 0. So those are solutions to that equation, negative 2 and 0. And they check that right here. They take 0 and substitute it in, and it's true, 0 equals 0. And then they take that negative 2 and substitute that in, with 0 being the y. And when you substitute negative 2 in, that's also true. So those ordered pairs both work. So those are the solutions for this 4th degree. Now, we know there's 4 solutions because the fundamental theorem of algebra. So the other 2 solutions are either imaginary or they're duplicates. It might be 2 solutions of negative 2 and 2 solutions of 0, or it could be 3 of 0 or something like that. But we know that these are the real number solutions. There's at least a real number solution at negative 2 and 0. And actually, the others are imaginary because we're going to learn in a minute that there can't be 2 solutions of either one of those. More on solutions of polynomial equations. Let's see. Find the solutions to this function and describe the end behavior. Well, it's a 3rd degree negative, so we know it's going to be up and down. And this has one solution. We see it cross the x-axis at 1. So x equals 1 is the solution for this equation, just looking at the graph. The other 2 solutions either imaginary or there's 3 solutions that are all exactly the same of 1. Describe the end behavior, up on the left, down on the right. Possible zeros, just 1. And then when you check it and you put that 1 in there, it does check with the math. All right. So if we look at this one, find the solutions to this function. x plus 6 to the fourth power. That's even, so we know both ends point the same way. It's a positive coefficient. We know it goes up, and it's graphed for us. But this has two solutions, two real solutions. One's at -7, one's at -5. All right? Don't make it real complicated. When you're graphing, trying to find real solutions, it's where it crosses the x-axis. What do we have over here? Yeah, -4 and, -2 and 0, the solutions here, because that's where it crosses the x-axis. So the solutions, I was checking those, possible zeros at -7, -5. Those are the two solutions. And then they checked them, and they both checked out. But we know they are because we can see it on the graph. Page 3. All right, even and odd functions. So we're going to talk about symmetry. A function whose graph is symmetric with the y-axis is an even function. All right, now I'm not talking about necessarily the degree of it being odd or even, the exponent. I'm talking about it. We call it something called an even function. The degree is not the same thing. So let's take a look at these. This is not an even function on the right. It has an even exponent. I'm not talking about that. I'm talking about the function itself being an even function or an odd function, not the exponent being even or odd. These are two different things. The function itself. This one is an even function. This is nothing. It's not even a function. It's not an odd function. It's not an even function. It's just a function. This is an even function because it's symmetric to the y-axis. So we look at this one. It's not an even function right now, but if I did this, now it's an even function because it's symmetric to the y-axis. The y-axis is a perfect mirror cutting it in half. Now it's an even function. Now it's not an even function just because I moved it over. Now it's an even function. That's really as simple as it gets on what's an even function and what's not an even function. But there's also an algebraic way, and I'll show you how to do that in a moment here. So let's do this. I'll show you the algebraic way to figure out if a function is even or odd. So if we have this function, f of x equals x squared plus 2. And we want to know, is this an even function? Well, if we substitute -x and it equals the regular function, then it's an even function. There we go. If f of -x equals f of x. What do I mean by f of -x? Well, if we take -x and substitute it in, see, I took out x and I substituted -x in more because that's what I said to do here, -x. What is -x squared? Well, -x times -x. It's a negative times a negative. That's just x squared, right? So f of -x equals, this is x squared plus 2. It's exactly the same. This is an even function. We checked it algebraically, and we can graph it. X squared plus 2. Yep, look there. It's symmetric to the y-axis. So we can see from a graph, and we can see algebraically that it is an even function because when I substitute -x in and simplify it, it equals exactly the same equation as what we started with. And I mean exactly the same equation. We'll see some in a minute that are not exactly the same. So they're not even. All right. Now, Oh, they did an example there, did they? So we'll look at that. We'll look at an example in a minute. A function whose graph is symmetric with respect to the origin. What do you mean symmetric to the origin? That means if you rotate it 180 degrees, it looks exactly the same. You have to rotate it 180 degrees to be exactly the same. So, y, click, y equals x to the third. If we rotate this 180 degrees, it still looks exactly like it does right now. Right? We can turn that upside down and it's still going to look exactly the same. And we can tell that because every point you can find here, like this, 1, 1 is a point. That means -1 is a point. That means it's 180 degree symmetry. That means everything you find over here, you find the exact same points over here, except they're negatives. So that is symmetric around the origin. Now, if I change it to this, it's not odd anymore because that's not symmetric around the origin. It's symmetric around this point here, but that's not the origin. So this is not an odd function. This is an odd function. So odd functions have to be symmetric around the origin. All right, so we can check algebraically on that also. If, oh, I'm right in there. F of negative x equals the negative of fx. Notice it's out front. That means everything is the opposite. Then it's an odd. Okay. So let's check one here. So if we have f of x equals, let's see, 2x to the third minus x. 2x to the third minus x. And we're going to give it the same test we did above, as we're going to substitute negative x. So 2 times negative x to the third power minus negative x. So what's negative x to the third power? Well, negative x times negative x times negative x. Write that down. We know negative x times negative x is x squared as a positive, and then multiplying that times another negative x makes it negative again, right? Because it was positive, now it's a negative. So this will be negative 2x to the third. Because it's negative x to the third, and that's being multiplied by 2. So it's negative 2x to the third. And then minus negative x. Well, when you subtract a negative, so that's what that simplifies to be. And if we look at it, we go, this was positive, now it's negative. This was negative, now it's positive. I don't like the way I did that. It makes it look like I drew a positive there, but there's not a positive there. This was a positive. I'm going to put a positive there. Positive 2x minus. So all the signs changed. This is an odd function. Because all the signs changed. So let's look at another one to figure out, is this odd or even? If we just have this, and we don't have Desmos open, we're not graphing it, we're just trying to figure out, is this odd or even? And so we've got 2, just like above, 2x to the third. 2 looks a little funky there. Oh, I don't like this eraser. 2x to the third plus x minus 1. All right, I'm trying to figure out, is this an even or odd function? Well, if I substitute negative x in, I've got 2 times negative x to the third plus negative x minus 1. And we know when we simplify negative x to the third and times 2, we end up with negative 2x to the third because we just did that above. Plus a negative x is just minus x and minus 1. So is this even or odd? Well, if I look at what's required for it to be even, it has to end up exactly like it started. Well, this is not exactly like it started. Because up here we've got 2, down here we got negative 2. Up here we got x, down here we got negative x. And this we have, this was negative 1. It's still negative 1. This is neither even or odd. I guess I should say nor odd. Neither even nor odd. Because while this changed and this changed, this is exactly the same. Every term has to either be exactly the same or exactly opposite. If you have any combination, then it's neither even or odd. Those very specific functions are even or odd. Very specific functions are even or odd. Without the negative 1, it was fine. It would be an odd function. But that negative 1 at the end, it is not even nor odd. So that's some great examples to have in your notes. Neither even nor odd. All right, let's go back and see what we do. So they have example here, x minus 1 to the third. See, that one moved over here. It's not symmetric around the origin, and it won't work algebraically because they started with, here's the one where they did x to the 1, x minus 1 to the third power, which equals x to the third minus 3x squared plus 3x minus 1. And when they substitute it in, they get negative x to the third, so that changed. Negative 3x squared, that stayed the same. So right there, it already blew it. It's not even nor odd. This one changed to negative 3x instead of positive 3x, but the negative 1 stayed the same. So this is not an odd function, and it's not an even function either. All right, so it's looking at this, and it says, let's investigate this. They did not give us the equation, so we're not going to substitute negative x in. But is this even, odd, or neither one? Well, it's definitely not even, correct? That is not symmetric over the y-axis. If we take this side and flip it over here, it should be up, where this is up. But if we turn this graph upside down, it should look exactly the same. So this is an odd function because it's symmetric around the origin by 180 degrees. So symmetric around the origin means rotate it 180 degrees. Take the top and the bottom and switch them. This is an odd function. Check answer. It's odd because it's symmetric to the origin. All right, this one, it just gives the equation. Is it even, odd, or neither? So if we substitute negative x in, negative x to the fourth power will just still be a positive x to the fourth power. Negative x squared is still going to be a positive x squared. But when you multiply it by negative 2, this should end up exactly the same equation. 4x, x to the fourth minus 2x squared plus 1. So this is even because it ended up exactly the same when you substitute it. So here's our lesson summary. What characteristics describe even and odd functions? That's pointing up, pointing down on the ends. And how does a constant or a coefficient affect that? Well, the coefficient can make it reflect downward, change that. The constant can make it skinnier or wider. And there's the little chart we made with the leading coefficients, positive or negative, even degree, odd degree. And then here's how to check if it is even, odd, or neither. Algebraically or looking at the graph. At y-axis symmetry, origin symmetry, or could be neither. So there's a nice lesson summary. Let's look at the assignment that goes with this first lesson. How does the graph of g of x equals x minus 3 to the third plus 4 compared to the parent function? Well, there's an x minus 3, so that moved it left and right, right? So it's negative, it moved it right. And the plus 4 moves it up. What? 3 units to the right, 4 units up. Here's another one. How does this graph compare to the parent function? So what translations happen? There's a negative coefficient out front. There's a minus 2 in the parentheses. What's the end behavior? It says without technology. If you want to check yourself, you can go to Desmos, but see if you can do it first without technology. This is a fourth degree with a negative coefficient. That should tell you all you need to know, because we made a little chart. That's an even, 4x to the fourth is an even number, and it has the coefficients, that's a negative. Is this graph even or odd? It's not neither, because that's not a choice. They only give us a choice of even or odd. So you got to look at that and figure out, is that even or odd and why? It's because it has respect to the symmetry to the y-axis of the origin. And determine whether this function is even or odd. So there you go. 5 problems there. All right, let's look at the last assignment for the week. We've used half our time, so we're doing all right. We're going to learn how are solutions connected to the graph of polynomial functions, and what key features can be identified from graphs of higher degrees. All right, so if we look at this equation, x to the third plus 3x squared minus 22x minus 24. Okay, let's put that on a bigger graph. Let's do that over here. Make that to the third, make that squared. All right, here's a bigger graph. Woo. When it goes way up there and way down, doesn't it? What do they show us? Okay, they just made it scale up to 45. So here we could change our scale a little bit. Let's do the x-axis from -10 to 10. There, kind of make it look like theirs a little bit. Okay, notice that the zeros represent the x-intercepts. So if we were trying to figure out, examine the graph and determine the zeros with a visual approach. The zeros are also the solutions. Let's see, there's one, there's one, there's one. So the 3 solutions, and it's an x to the third, so there's only 3 solutions, is -6, -1, and 4. We just found the 3 solutions without having to do any kind of long division. No polynomial long division, but we found the solutions just by graphing -6, -1, 4. So as the zeros of the function, 4, -1, -6, can be confirmed by, you can substitute them in there and see that they do all equal 0. So that confirms it, which means you can write it in factored form, x minus 4x plus 1x plus 6. So that's the factored form of the exact same equation. All right, let's go page 2 here. All right, I like this. Determine the zeros of f of x equals x minus 2, x minus 5, x plus 1. Oh, I'm going to put this in our notes just because we need to continue practicing this kind of stuff, because this one is so easy that we look at it and our mind freaks out going, this has got to be harder. What am I missing? And you try to make it really hard when it's not. Say, determine the zeros and describe the end behavior. X minus 2, x minus 5. It's in factored form. This is some kind of x to the third equation. And if we multiply those back together, we can find out what this is over here. What is this whole function? But we don't have to if we're just trying to find the zeros and the end behavior. The end behavior already knows that we have an x times an x times an x. So that's going to be a positive x to the third equation, which means it's going to go down on the left and up on the right. That's the end behavior, because it's a odd number up here and it's a positive coefficient, because these are all positive x's. But what's the 3 solutions? Remember, we find solutions by setting them equal to 0. So x minus 2 to times x minus 5 times x plus 1 equal to 0. So that means x minus 2 equals 0, or x minus 5 equals 0, or x plus 1 equals 0. So the solutions are x equals 2, 5, and negative 1. Because x minus 2 equals 0. So x is 2. 2 minus 2 equals 0. 5 minus 5 equals 0. So x is 5. Negative 1 plus 1 equals 0. You could also find it by subtracting 1 from both sides. Yeah. So there's the solutions. 2, 5, negative 1. There's the end behavior. Don't make that hard. Don't make that hard. When they give it to you in factored form, say, yay, thank you very much. Because that makes it real easy to find the solutions. And if we graph that, we can graph it in factored form. We don't think about doing that very often. Y equals x minus 2 times x minus 5 times x plus 1. Look, there it is in factored form. Look, there's our 3 zeros, negative 1, 2, and 5. That's exactly what we came up with. So graphing it's going to tell us the same thing. No, I need to change this funky negative 10. I'll do this from negative 10 then to a positive 10. So it looks a little bit more square again. But yeah, there's the solutions. And we just graphed it in factored form. And look, it goes down on the left and up on the right, just like we said, because it's an x to the third. So there's our end behavior. It's all good. It's that easy. We love it when it's in factored form because it gives us most of our work. Here's another one. X plus 2, x plus 3, x minus 1, x minus 3. Oh, 4 x's. This is an x to the fourth. They're all positive. So you multiply them together, it's going to be a positive x to the fourth. Both ends are going to point up. And we know the 4 solutions. Negative 2, negative 3, positive 1, positive 3. Because when you set them equal to 0, that's the 4 solutions you get. That is the zeros. Don't make that hard. There's the W that it makes with those 4 zeros. Example 3. Okay, this one's a little trickier. Let's go ahead and solve this one on paper. But it works exactly the same. So this has 3 x's. We have a 2x, a negative x, and a 3x. That would be, if we wanted to find, again, this would be some kind of x to the third equation. But is it going to be a positive or negative? We've got to know the end behaviors. So you've got a 2, a negative 1, and a 3. So 2x times negative x times 3x would be what the first term is, because it's the first term of each of these. And when you multiply those together, you get negative 6x to the third. That's what our equation is going to start with. And then it'll go with whatever the rest of the equation is. Negative x to the third. So this is going to go up on the left and down on the right, according to our little chart. Negative odd numbered exponent. Now, what are the solutions? Well, we have 2x minus 1 equals 0. We have negative x plus 3 equals 0. And we have 3x minus 4 equals 0. What's the solution here? Add 1. 2x equals 1. Divide by 2. X equals 1/2. There's one of our solutions. Negative x plus 3. I'm going to do something weird. I'm going to add the x on the other side just to make it positive. 3 equals x. Oh, there's our other solution. So we got 1/2. We have 3. And what's our third solution? Add 4 to both sides. So 3x equals 4. Divide by 3. 4/3 is our last solution. There's our solutions. Let's graph this just to check this out. Let's see, I can just copy that right there. Oh. Copy. Paste. See, we said there's a solution at 1/2. We said there's a solution at 3. And we said there's a solution at 4/3, which 4/3 is 1.333, because 3/3 would be 1, which leaves us another third. So there's the 3 solutions. And look, it goes down on the right, up on the left, because when you multiply those together, you'll get that negative 6x squared, plus a bunch of other stuff. But that confirmed what we did algebraically on paper of finding the 1/2, the 4/3, and the 3 as our solutions. 1/2, 3, 4/3. There it is. And they show the same graph that we had. Odd degree up on the left, down on the right. Page 3. How does the root with multiplicity change a graph? Okay. So if I have a graph, I like this one right here. So let's play with that. I'm going to kind of duplicate that on paper here. We're going to pretend this is the exact same graph. It's close. And what do we see? We see that right here at -5, and right here at -3, and right here at -1 are all places that this graph touches the x-axis. This is, look at this. It's pointing up. This is an even degree function, but we only see 3. We only see 3 real solutions, but we know it has to be even. Wait a minute. I want us to stop and think about that for just a moment. We know it's an even function because it does point up on both ends. We see that. So it has to be a 2nd degree, 4th degree, 6th degree, 8th degree, one of those even numbers. We see there's 3 real solutions because it touches the x-axis in 3 places. And what do we know about imaginary solutions? You're like, oh, well, if it's a 4th degree, then there's an imaginary solution. That'll be the 4th. That doesn't work. Because what we know about imaginary solutions is they never are by themselves. They're very timid. They're very afraid. They're very anxious. They never go anywhere by themselves. They always come in pairs. There's always pairs. If you have one imaginary solution, you have 2 imaginary solutions. So if we see 3 solutions here and we know it's an even number, if there's imaginary solution, that means there's 2. That means there's 5, or there's 7, or there's 9, or there's 11. I don't think that's the solution. It can't have imaginary solutions because they would be in pairs, which would keep it odd. But I want to show you one thing that I noticed about this graph right away. Let's look at what's happening right there. See what's happening right there? It didn't cross the x-axis. It bounced. That means there's 2 solutions there. What? Yeah, this is a 4th degree, apparently, because the solutions are -5, -3, -1, and -1. This is the equation x plus 5, x plus 3, and x plus 1 squared. Because when you graph something, if it has multiple solutions that are even number, like 2 solutions or 4 solutions, it will bounce. Duplicate solutions. I'm going to say even numbers. You've got to do like 2. Will bounce. Question and answer. It'll get to that. Type and answer like, which brother is my favorite? So while we're talking about that, we should also say duplicate solutions. Odd numbers. What I mean by that, I mean maybe you have 3 solutions that are all the same. Will cross, but I'm write this how it makes sense to you. But wave, I'm going to say wave. Because if there's 3 solutions, it may cross, but it's going to kind of do one of these numbers. It's not going to just straight across. No, it's not going to do this. It's going to do something like this. Right? It's going to be a little wavy. This is one solution because it just went straight across. This just went straight across. If we had one of these that just kind of curved over like that, we'd say, oh, there may be 3 solutions there, or 5 solutions, or some other number of solutions. It'll either bounce if there's an even number of solutions, or it'll make this little odd. So let's play with that just so we better understand it. Let's go back to Desmos, and let's simplify this. Okay, we're just going to make this x minus 1. And then we're going to say x minus 2. Okay, right now we've got 2 solutions. One's at 1, one's at 2. But, well, actually, let's spread those out a little bit. Let's make this a plus 2, so they're not right next to each other. Let's say we've actually got 3 solutions at x plus 2. Here's a second one. Notice it bounced now when there's 2 of them there. Let's add a third one. X plus 2. Ah, see? It made that little wave as it crossed over the x-axis. There's only 1 solution here, so it went straight across the axis. Over here, there's 3, so it crossed, but it kind of waved as it went over. Kind of flattened out a little bit. So you can see the difference. So this is a 4th degree. This is a 4th degree because there's 3 solutions here and 1 here. That's why it goes, both ends go up because it's a 4th degree. If we change this to an x minus 1 times an x minus 1, see that's 2 solutions. I can also just do this. Let me just say, oh, not that. X minus 1 squared. And let's change this to be to the 3rd power. So there's 3 solutions here and there's 2 solutions there. One of them bounces, one of them crosses, but kind of squiggly crosses. Let's change it to a 4th degree. What does that change? Oh, that didn't make it 4th degree. There we go, 4th degree. Now look, it's a little flatter, kind of like a parabola and a 4th degree. So we can say, oh, okay, so that means there's at least like 4 or 6 or 8. You know, if we change it to a bigger number like 8, just flattens out more. But we know that there's multiple solutions in an even number, either 2, 4, 6, 8, something like that. And if we change this other one to be like 13th instead of 3, look, it flattens out too. It's a wavy cross. But that's the difference. We can tell a lot about the graph on how many, that there's multiple solutions. If we look at just the graph of this, we really don't know how many solutions there are. We know that there's probably more than 2 because that's pretty flat. And this is probably more than 3 because that really flattened out. And turns out this actually has 21 solutions. There's 8 of them here and there's 13 of them here. But we'd never be able to guess that. But we can tell that there's more than one, that there's multiples at that. So that's really what it's very useful for us to let us know when we see an equation like this, that there's at least two solutions there. One solution. This is a 4th degree. That's why it's pointed up when it only shows 3 solutions. Because there's a multiplicity. Multiplicity. All right. Oh, and here they show us the equation down at the bottom. Look, there's x plus 1 and x plus 1. There are 2 solutions there. Over here, look, it bounced off at -3, way at the top of the graph. There's 2 solutions at -3. So that's kind of cool. It says, given the cubic, x plus 1 squared, x minus 2, sketch the graph. Okay, so we would go to -1 and know that it bounces off of it there and go to +2. Oh, do I have it? I'm going to draw a graph for that. I don't have another sheet of graph paper here. I need to get some more graph paper. Let's see if we can sketch that at -1 and +2. So if we have this, and wants us to sketch the graph. Let's see. We know there's x squared over here. There's two x's, and there's a third one. So this is an x to the third equation. So we know it's positive. So if it's positive, it's going to go up on the right and down on the left. So we know, let's see, x minus 2. So we know we have a solution there. X minus 1. So that's x plus 1. So at minus 1, we know there's a solution there. On the right side, we know it's going up. We know the left side's going down. Now, what do we know about this is there's two of them, so it's going to bounce. So this will come down wherever it comes down to. And when it gets up here, it's just going to bounce. Actually, we know this is going to cross at -2 because 1 times -2 on the right side of the equation is going to end up with -2, and there's going to be stuff in the middle. We don't know what all the middle stuff is, but multiplying the numbers together will get us the y-intercept. So this is a graph that's going to bounce there and cross there at 2. -1, -1, and 2 are the three solutions. So let's throw that in Desmos and see how close we got. See, it probably dips down farther before it crosses the y-intercept there, but we're going to go with that just as a sketch, because as a sketch, that's totally appropriate. Okay, so we said it was x plus 1 squared times x minus 2 was the equation. Yeah, there it is. There's the one that it bounced off of. There's the 2. Crosses at -2. And it did dip down farther. I said that it probably did. I said this probably dipped down farther. And that was the only difference between our graph and theirs, is this dips down farther and it's coming up farther. But that's pretty good. If you had an assignment that said sketch the graph, 100%. That because the important parts are, did you get the right solutions? Did it bounce? Did it cross? That's what it's wanting to know. And in this case, we got the y-intercept correct as well. Oh, let's see. Given this cubic, x minus 3, 10x squared plus 29x plus 20, and one of the roots is x equals -5. So they would say, all right, we can use long division. And since it's not -5, we'd take x plus 5 and divide it into there. And they want us to find the other roots and then make the graph of that. Well, let's let them do the long division for us. X squared plus 5x plus 4. Does that factor? It does. So it end up x plus 5, x plus 4, x minus 1. So we have 3 roots at -5, -4, and -1. And we know it's x to the third, so it's going to go down on the left and up on the right. So we would start down and grow up through -5, go down through -4, and back up through -1. Up through -5, down through -4, back up through -1. Using the long division to find all of the zeros, to find all the roots. X to the fourth has a root of x equals 2 with a multiplicity of 2. So they tell us there's 2 of those right off. And they want us to use, again, polynomial long division. We're not gonna do that because of the interest of time. I don't know how much longer this lesson is, but I don't want to run out. Let's see. Oh, there's another page at least. Graphing with technology. So you may need to customize the view, right? Because it may be off the screen what you need to see. You may have to change the numbers on what you're seeing. I'm seeing from -8 to 7 on both x and the y right now. You may have to do that if you're graphing it. Make sure you know how to use the shift. So 5x to the third instead of 5x3. And if you need that, take a screenshot or whatever if you need to turn it in. And you can use the help menu for any other functions. Like on Desmos, you may have to use the little menu down here to get some of the fancy functions. You need a square root or something. It has that. Okay, it says this one wants us to use graphing technology and then describe the end behavior. So I'm just going to copy that. Now, when you copy it to Desmos, it loses all of its exponents. See, that's just -4x4. I have to tell that this is an exponent. Okay. So I can highlight each of those and shift 6, and it makes them exponents again. -4x to the fourth minus x. So you always double check if you copy and paste that you have it correct. And it wants us to do what? Describe the end behavior. Well, it's a fourth degree and it's negative coefficient. So both ends go down. And we have two real solutions, and they're not really nice numbers. Those are very nasty numbers, right? Because that's, I'm sure this is rounded. It's 0.70876, blah, 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 but we've rounded it to 5 decimals. But that's the end behavior. All right, page 4. This should be the last page. Key features. Average rate of change, increasing versus decreasing, minimums and maximums. All right, we're going to use the graph we have right here. I'm gonna fix it just a little bit. I'm gonna try to fix this where it goes down a little farther, like we had it a minute ago on the screen. So we're gonna say this goes down to like right there, and that's going to be at -3. Okay, so if we said average rate of change, what is the average rate of change between? Now you got to tell it when you say average rate of change, between where and where. Tell me where to start. From x equals -1 to x equals 1. Okay. Well, x equals -1 is right here. That's the point -1, 0. Right? And x equals 1 is right down here, which is the point -1, 1, 2, 3. I'm sorry, +1, -3. So this is the 2 points. And it wants to know the average rate of change, which means if I took my ruler and I made a line that connected those 2 points, what's the slope of that line? Because average rate of change means slope. Slope. Average rate of change is slope. Don't write with big green markers because they don't make nice letters. So how do I find the average rate of change? Well, the slope formula, m equals y2 minus y1 over x2 minus x1. That's one way to do it. The other thing you can do is rise over run. Let's use this formula first, since we have the points. y2 minus y1. So let's take -3 minus 0. And then let's take 1 minus -1. Since this was y3, this has, I mean y2, this has to be x2 over 1 minus -1. -3 minus 0 is -3. 1 minus -1 is 2, so it's -3 halves. -3 halves. That is the answer. We could also do it by rise over run. How much did it rise? It went 1, 2, 3. It went down 3. And then it went over 2. 1, 2. It went down 3. And it went over 2. -3 halves. Same thing. So you need to do it with slope formula if you have the points, or if you have the graph, you can do rise over run to figure out the slope. We're talking about just drawing a straight line. Slope between 2 points. Average rate of change. It can be very simple. Maybe they'll say, what's the average rate of change from x equals -1 to x equals 2? How about this one? Who can get that quickly? Anybody? What is the average rate of change from x equals -1 to x equals 2? Oh. You doing rise over run? Are you doing slope formula? Or do you need to do anything at all? Where is x equals -1? Well, that's this point here. Where is x equals 2? That's this point here. What's the slope between those two lines? 0. There's no rise at all. It's 0 over 3. 0. They like putting those on tests and stuff too, because people go, oh, I don't know, and they come up with these answers. It's -4. It's like, no, it's 0. They're the same y. They have the same height. They're both at 0. All right, other things they would like to talk about. Let's draw it back. I'm going to make another graph because I've already drawn that one up so much. If we have 1, 2, 3, 4, 1, 2, 3, 4. We got a graph that goes right here, back down. Okay, we have this graph here. And it wants to know minimum and maximum. Well, what's the minimum and maximum? That's the minimum and maximum, right? Because this goes on forever. And this goes on forever. However, there's something called the relative minimum and the relative maximum. So we're going to cover this again. I may have covered it before. Again, I need to kind of straighten this out there for a minute. I want those points to be at nice, even places. I want this to go like that. All right, so this is the point 2, -3 right here. That's the lowest point. This is the point -2, 1. This is a relative minimum, which means if I just look at part of the graph, just relative to this area of the graph, that's the lowest point. Relative minimum at 2, -3. And there's a relative maximum, which means if I ignore that it goes on forever, there's a relative maximum at -2, 1. Because at that point, -2, 1, that's the highest point of the graph. If I ignore that it goes forever, just ignore it goes forever, and ignore that it goes forever this way, that's the minimum and maximums. Does that make sense? That's the highest point and lowest point of the roller coaster. As long as the roller coaster didn't go forever into the sky until I run out of oxygen and die. All right. The other thing, increasing, decreasing. I think this will be our last thing. When is this graph increasing? If I had this on a test and I said, when is this graph increasing? How would you know how to answer that, right? These questions are always based on the y. Your answer is the x's. And we'll talk about what that means. Based on the y, when is this increasing? Because if you look at it and say, well, the x, it goes from -4 to -3, -2, -1. But, you know, it's increasing all the time, the x, if we go like that. No, we're talking about based on the y, when it goes up and it goes down, when is it going up? Well, if I look at it, it's going up forever till it gets right there. Right? And then going up. If I start on the left, just like we read from left to right, if I go from the left this way, This graph is going up, 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 up. But after that, it's not going up anymore. That's the peak top of the roller coaster for that point. So my answer is based on the x's. So when the x is from negative infinity until the x gets to negative 2, it's increasing. But notice when it gets to negative 2, it's not increasing any longer. It stops. It's flat. The slope is 0 at that very, very point. But if I look over here, I can see, wait a minute, it's also increasing here. And from 2 to infinity and beyond, yes. When x gets to 2, as the graph goes past that, it's going again, increasing. So this is my answer for increasing. Let me kind of box that out. There are 2 intervals where it's increasing. We can see that on the graph. It's going up over here, then it's not, then it's going up over here. So it's increasing from negative infinity to 2, and it's increasing from 2 to infinity, which means it's decreasing where? Well, look here, it goes, it was up here at the 1, but it goes all the way down to the negative 3. So it is decreasing from x equals negative 2 until the x gets to 2. So these are the x's. So we're using the x numbers to mark where it's happening at, but we look at the y's. The y's are going up, the y's are going up. Oh, once the y gets to 1, now the y is going down to 0. It's going down to negative 1, negative 2, negative. Oh, now the y is going up again, 0 all the way to infinity. But the x is what marks the area. Well, stop. Don't go past there. That's where it stops. Now it doesn't go up after that. It goes back down. So this is great to have in your notes too, to know how do I write that? Well, it's based on the x's. From where to where on the graph is it going up? From where to where is it going down? And a lot of times it's more than one answer. Like this is going up 2 different places. So maximum, minimums, increasing, decreasing. So they're pointing out this one here, increasing, decreasing, increasing, decreasing, increasing. There's 3 places where this graph is increasing. Only 2 where it's decreasing. So don't confuse yourself. It's not too bad. Minimums and maximums. This has 1 minimum. This has 2 local maximums or relative maximums. Local and relative, same thing. 2 local minimums, but it really doesn't have a max or min because they go to infinity. Average rate of change between negative 1 and x equals 1. At negative 1, where's way down here? It's at negative 4. At 1, it's up at negative 2. So it rises 2 and runs 2. That's got a slope of 1 between those 2 points. Check your work. Calculate the average rate of change. This one, you just have to substitute them in there. Substitute negative 1, substitute 1, and that'll get you your y values. And then you can use the slope formula, y2 minus y1. Or you could graph that. Lesson summary. Whew, we made it. Made it to the end. Okay, the roots, zeros, solutions are wherever it crosses the x-axis. When it's written in factored form, that gives us the roots. In behavior chart, we have that in our notes. Average rate of change, there's that formula for 2 points. The x's and y's of 2 points. You can figure out the average rate of change. Increasing versus decreasing, minimums and maximums. Let's see the assignment that goes with this one. What are the zeros? Oh, good. It gave it in factored form. That one's easy. One factor is x minus 7. What are the other ones? Oh, that's a flashback to polynomial division or Desmos. hopefully they're real solutions and you can get from decimals. What's the average rate of change from 0 to 1? So you can substitute 0 in and substitute 1 in, or you can graph that and look on the graph at 0 and 1. Estimate the average rate of change between x equals 0 and x equals 2. Wow. So that goes from 1 to 11. And it goes from 1 to, so it rises 10, runs 2. And what are the zeros of this function? We learned that. That's pretty simple. All right. We were running like our pants are on fire today. Kittens available. That just popped up on the screen. There's a student's got kittens they're giving away. So if anyone's need kittens, if anyone loves kittens, then tell Miss Dean, because she's got one of her students that's giving away kittens. So there you go. Lovely stuff. All right, guys. Next week we just have one lesson, and then we're going to have our discussion-based assessment all next week. So something to look forward to there. And then semester final the week after. So we're almost done with the semester. If there's anything you're missing, if you're missing anything, get it turned in right away, because I don't want you to end the semester with missing assignments. And anyways, we will see you guys later. This is an 8A Friday if anyone needs to be here. Wednesday and Friday. See you next time.